is better off. I'm not sure.
If it doesn't rain.
If it doesn't rain, otherwise, please wait.
Yes.
Sorry, guys.
And the meeting's been sorted.
Got it.
Got it. Okay, so today we wanted to overviews. So NRGR, sorry, it's an acronym. The title is not very welcoming. It's non-relativistic general relativity. So you might think it's not similar, but I will try to argue that it is not. So non-relativistic general relativity. So non-relativistic in the sense not small velocity general relativity. So this is one of the many tools, but definitely not the tool. It's one of the many tools that is used to compute perturbatively the dynamics of the body problem. And it has been quite successful, and I will try to give you the basics of what the tool is, and maybe induce some of you to work on it, and possibly see what are the main obstacles, the main challenges to move this method to higher perturbative order than we've done so far. Oops. Yes. Okay. So the basic idea was laid down already almost 20. Oops. I need to. Almost 20 years ago by this seminal paper by Walter Bruberger and Ira Rotten. So basically they wanted to recast the computation of the standard post-Newtonian approximation to general relativity in a field theory language. And the basic observation that allowed them to do this is the following. Is that when you think about the binary system, you have a clear separation of scale. So I will use this bunch of words, separation of scale, many times. And the idea is that you have a black hole or a neutron star, which is a contact object. It's the size of kilometer for the masses we're interested in. And you know, the masses, they put a cutoff, they translate into a frequency. I mean, the size of the object translates into the maximum frequency you can detect. So it's the detector that tells us what is the masses we see. It's not something we can change freely, because the detector, it has a definite frequency band, and so the minimum frequency gives you a maximum mass. So LIGO cannot see masses larger than 100 square masses. Still, even for 100 square masses, the typical size of the object is order of kilometers, tens of kilometers, and the separation is larger than that by factor d squared. It's just the Kepler's law. The Kepler's law tells you that GM, which is the size of the source, is smaller than the distance between the two bodies by factor d squared. And then when you look for far away, typically from the observer distance, the object looks like a point which is no longer a fundamental particle, but it's a point which is very hairy and endowed with a lot of multiforms and structure. For instance, the quadrupole. But of course, the quadrupole is just one of the many characteristics you can use to define your binary system. And the scale of variation of the wavelength emitted, which is r over v. And again, v is smaller than 1, v is the typical velocity of the internal velocity of the binary system. So this is this wavelength is much larger than the separation, which is much larger than the size. So this separation of scales allows you very neatly to define an IFT-UNESP for this problem. So and then also, Bruberger and Rossen didn't have to invent everything from scratch, because this was already used to treat QCT of heavy quarks. So in the prototypical theory, there were heavy quarks that behave like black holes for us, and they exchange gluons, and this was already used to study this kind of theory. Okay, sorry, this paper is subsequent of this, but the NRQCT, non-relativistic QCT, precedes NRGR. And then, of course, this can be, it was immediately generalized for spinning objects. What I will say today will only apply to non-spinning black holes, and I will not talk I will say almost nothing about the dissipative sector. I will only focus on the conservative sector. Just because, you know, if I want to do something pedagogic, I have to restrict and give the basic ideas, focusing on one specific aspect of the dynamics. So the idea then is the following: that due to the separation of scale, okay, we can forget the size of the object. We treat of fundamental particles, point-like particles, and what is and we have two theories. The two theories, I mean, if the only one fundamental theory is the theory of general relativity coupled to black holes. That's physically the only theory. But at the level of our effective theory, we want to break it into two smaller theory. Each of the two are much simpler than the full GR coupled to black holes. So we have a near zone theory and a far zone theory. So in the near zone, you treat each of the two black holes as a worldline particle. So the black hole is propagating through spacetime, but is actually maintaining its mass and its individuality. It's not like in particle physics where you change the number of particles because particles are created and destroyed all the time. No, black holes, they live on God-given world lines. They might have spins, even though I will not treat the spin, and they might have degrees of freedom attached to the world line, like for instance a spin-induced quadrupole, and they might have degrees of freedom related to the finite size that in this language are parameterized by higher order terms of the curvature. So here you cannot have a Ricci term or a Ricci scalar term because they are zero, the equation of motion, because we want to compute the Ricci term and the Ricci scalar of the space-time on the world line of the particle. Of course, we don't want to compute the Ricci on that particle, which is sourced by that very same particle. The Ricci of the other sourced by that particle on particle one is clearly zero, no? Because the Ricci is non-zero only when you have a non-zero energy momentum tensor. So there is no space in this theory for a Ricci scalar or a Ricci tensor because they are proportional to the energy momentum tensor of the other particle, which on the top of particle one is zero by definition. So the leading order say non-geodesic term is a Riemann square. The Riemann can be non-zero outside the other part. And so, and these will argue that are responsible for parameterizing finite size effect. So this is a near theory in which you have two individual black holes interacting by emitting gravitational holes. And then there is the far theory. The far theory, you have a blob, the two black holes, they form an object with multiples. And this object will have a total mass, which in first approximation will be given by the sum of the two masses, but of course with also contribution from the kinetic energy and so on, and higher general relativistic, special and general relativistic corrections. Then we have a spin that will couple to the gradient of a specific component of the metric tensor. So here the mass coupled to the 0,0 polarization of the metric tensor. The spin couples to the first gradient of HI0, and then you have all multiples. You have the quadrupole, the octupole, not like you could do in electromagnetism. Just that in electromagnetic thing starts with the dipole. Here the dipole is not emitting. So you have the quadrupole, the octupole, and again the basic observation is that this term is enhanced with respect to this term. The quadrupole is enhanced with respect to the octupole by a factor of V. Why? Because this is the Riemann. This is some specific polarization of the Riemann. This is a gradient of the Riemann. So a gradient of the Riemann introduces 1 over lambda, the wavelength of the wafer. Whereas a higher moment of the source introduces the size of the source. So this object is suppressed with respect to this object by the size of the source divided by the wavelength of the emission. And you remember, the wavelength is exactly the size of the source divided by V. So there is a natural, this makes sense as a perturbative expansion. The octupole is suppressed by V with respect to the quadrupole, and so this is the magnetic quadrupole, which is the same order of the electric octupole, and so. But this is an expansion that makes sense, an expansion in powers of V. And so you see, you have this ubiquitous small parameter V that relates theories at different scales. So what is the bulk theory? Of course, we take general relativity, and of course we want it to gauge fixed because at the end we want to write a Green function for the we want to write Green functions for the graviton, even though everything is classical. You shouldn't call it graviton, call it gravitational mode. And so we need to gauge fixed. And so what's the state of the art? So in this framework, a bunch of German people, they managed to write down the 5 PN. So 5 perturbative order beyond Newtonian. So the Newtonian, 1 PN is next to leading. So they get to next to the 5 leading order to get the perturbative description of the potential, which is mediating the interaction between these two particles, with some caveats. I mean, this 5 PN is not fully concluded. I mean, they computed most of it, but not quite. They computed all of the near zone contribution. I will specify what I mean by near zone contribution. And we have been focusing up to 4 PN. We got the full result, near and far. In 5 PN, we have been focusing in a series of papers on the far zone contribution. So I will tell you why it makes sense to split the potential in these two contributions, and why it's logical from the point of view of computation and also from the physical point of view, to split the contribution to the two-body dynamics to something which is due to the interaction of one particle with the other, and something which is due of an interaction of this composite object with itself. So there will be the two contributions will be important for the dynamics of the two-body system. And basically, all of my talk is to try to explain to you the interplay between these two contributions. Okay, just to wrap up the phenomenological picture of where we are so far. So if you want to write an effective Lagrangian that includes the dynamics of two-body motion, so you start with a say less than Newtonian term, which is the total rare mass. Then you have the Newtonian term, kinetic term plus potential. Sorry, this is the Lagrangian, so kinetic term minus potential energy. And then you have 1 PN correction, 2 PN correction, and so on. And because, as Maria said this morning, because of the virial theorem, you see all of these terms, they appear at the same positonion. So P to the 4 is the same positonion order as V square over R, and the same positonion order as 1 over R square, just because of V square is Gm over R. Here, I don't write the powers of G. So you see, now the 5 PN is completed with one caveat that I will tell you. And 6 PN is done up to some order. 6 PN is done only to G to the 4. And then there is the orthogonal way of approach is to study a relativistic scattering. So V is not a small parameter, the velocity is whatever, and you just count power of interaction. And so 0 PM is 2 free particles, 1 PM is actually Newtonian, it's 2 relativistic particles exchanging G to the 1, then G to the 2, G to the 3, G to the 4. G to the 4 has been solved by 2 different groups in 2 different approaches, by the California group and by another German group. And still there is some caveat, and the star here and there have to do with the fact that the far near zone contribution will be fully nailed down. The far zone contribution has not been fully nailed down, and I will tell you why and how. So there are some issues at G to the 4 or at 5 PN that are related to the proper accounting of far zone contribution. And basically, I will try to lay down in this talk the basics of how we understand the interplay between near and far zone contribution. So my former student Gabriel will be here next week, and then my collaborator Stefan will be here starting from next week. So they will give you more specific talks about these issues I'm just telling you today. Okay, and so just to make a bridge with what Maria was saying this morning, so at the end of the day, let's forget about measuring down for a moment. What we need to do, we want to compute 2 functions, the energy and the luminosity function. So the energy for and let's specialize to circular orbit, so no spin, circular orbits, just to make it simpler. So the energy of a circular orbit binary system is minus the kinetic energy. Okay, this is not the typo, because it's kinetic energy plus potential. Potential is minus twice the kinetic energy, so the total energy is minus the kinetic energy. We are on circular orbit, so potential energy and kinetic energy are not independent. And then there are all sorts of corrections that go as V square, V4, V6, V8, and so on. And the coefficients of these V square, V4, and so on corrections depend on the symmetric mass relation, cannot depend on the total mass because this has to be dimensionless, so can only depend on this. Will depend on spins in dimensional units. Spin divided by square is dimensionless, so it can enter this, and so on. And then you have the luminosity function, which is dimensionless because G Newton is a converter from mass to length. So if you forget G Newton, this is mass, length is the same thing, divided by time, which is length, so this is dimensionless. And it happens to be V to the 10 and reading order, and then we have all sorts of correction, again, with some unknown, in principle, unknown coefficients that we have to find. Then there is a feature that the luminosity function can also have odd power of A, just heuristically, because energy is the energy of circular orbit, must be time reversal symmetric. So it can only have V square, V4, and so on. There is an exception to this rule. Whereas the flux is natural that it can also have odd powers of V, because the flux is the energy emitting per unit of time is certainly not time symmetric. Okay, so I will try to argue. I mean, I will just tell you that if I know these 2 functions, energy of circular orbits and luminosity function in circular orbit, then I know how to compute the wave. So what is the state of the art at the moment? So there is the 4 PN energy has been computed by us among other people, and the 4.5 PN of the luminosity has been computed for circular orbit. for in the 4PN in general, for circular orbit specifically the 4.5. So at the moment we know these two energy luminosity function up to 4.5 PN. There's no 4.5 PN for the energy, so we know it's 0. And we know the luminosity up to 4.5 for circular orbits. So why these two functions are enough? Well, because this is the phase is the integral of the angular velocity, tautological. And now we plug in the dynamics. We just make a change of variable, which mathematically is trivial, but physically it encodes these two functions into the determination of phase. You see, the dt, which is here, and so this is omega, and we write the dt as a dE in dV divided by luminosity, which is dE in dt. You see, all the differential simplifies, but then we related this integral over time to an integral over the variation of the energy function and the luminosity function. So if you know these two functions, then we know how to compute the phase, and then we know the truth. So this is the basic bridge between computing the dynamics and computing the wave. Okay, because the phase of the waveform just inherits twice the orbital phase, and the orbital phase is completely determined by the energy and luminosity function. And then, of course, there are different ways in which you can resum or expand each of the two. For instance, you can expand everything in the numerator, and you see there is a leading term, which is 1 over v to the 6, and then here you have v to all sorts of correction. That also means that if you want to keep under control the error on the phase that you compute in this way, you better include at least v to the 6 corrections. Otherwise, you have v to some negative power integrated, it is supposed to give you a large error. So v is small. So unless you add correction that make here v to the positive power, you will have a huge offset on phi. Of course, there are smart ways to resum function and to make it more precise, but this is really the broad picture. You really need high order terms. Otherwise, you make a big error in the phase, and then when you go and correlate with the data, you're making a big error, and you screw up parameter estimation. Okay, and so these are the post-Newtonian coefficients of the phase of the wave. So in particular, at every order, you get new physical, qualitatively new physical effects. For instance, at 4PN, you get absorption, that gravitational waves are not only emitted, but part of them is also absorbed by the binary system itself. At the v to the 10, you get tidal reformation, so that the sources can not only absorb, but they can also oscillate. You might think that the things are related. The things can oscillate, they can also absorb, vice versa. Question.
Just a question. What PN waves do they do not include absorption?
The absorption has been computed long ago, actually. You can take from some other paper, and it has been computed more than 10 years ago. Again, for also for spin, yes. But I think spin, yes. And the 4.5, they didn't solve in the generic case, but they solved for the luminosity function for circular orbits.
Does absorption change the black hole mass?
Yes, of course. Absorption, it means, yes, exactly.
It's also the low PN spin. Sorry, absorption with spin is a low PN.
So yes, this is all without spin. Yes, so it's 4 PN in the spinless case. With the spin, it's 2.5 PN. So the effect is yes. And so there are, you see, at any PN order, if you break things in PN, at any PN order, you have a new surprise, a new qualitatively different effect that you didn't have at the previous order. So it's nice to have an analytic control because you can really check if GR is behaving the way it's supposed to be. In numerical relativity, everything is lumped together, so it's more difficult to separate. Okay, more questions on this, and then I go on with more hardcore stuff. This was kind of phenomenological picture, broad picture.
Just on the last thing, that you neglect the variation of the amplitude here.
Yes, yes, this is just, of course, the amplitude, you can monitor that too.
Yeah.
And of course, the amplitude is related, okay, I don't have here the formula, but you can guess.
You will come back to that later.
Not really.
Oh, okay.
Well, you can guess it from here. Let me show you the diagram. Since you are a theorist, you know that here there is a dh square in this term, and here there is a h couples to q. So basically, you just solve h given by the green function times q. So basically, if you monitor q, you know the amplitude of h. But so that's additional information that you can get from the equation of motion. But what I showed you in this other slide was just a shortcut to compute the phase without solving in all detail the equation of motion, which you can also do. So what's next? Okay, so these are near zone cycle of the interaction. So basically what you have one particle which is solid as rock. It is not basically its momentum is way larger than the momentum that is exchanged to particles. So the gravitational model is taking a little bit of momentum out of this because this black hole is basically infinitely massive. But we know the gravity gravitates, so gravity self-interacts, so this is also a contribution to the potential. So this will give the Newtonian potential, this will give one of the G correction to the Newtonian potential, and this is also a G correction to the Newtonian potential. This is basically the Newtonian potential square. So these are just some of the processes that contribute to the near zone potential. So, but this is particularly nice to look at because look, this is also the leading order diagram that you have to include from this non-geodesic word line piece. This is a piece. I mean, if you vary this, it will give you the geodesic motion for the word line. This will give you a non-geodesic. Suppose we forget the spin. So you vary the word line, it will give you the geodesic. When you vary the word line action in addition to this coupling, this will give you a non-geodesic term in the equation of motion that with the upper coefficient that I didn't write here, the coefficient is not 1, will give you the effect of finite size. If you want to translate in interaction between one particle and the other, well, this one particle, the linear effect of this is 0 because it's a Riemann square. So you have to linearize each of the two Riemann. So this is at least involves two gravitational modes. And so since it's a Riemann, it involves two derivatives of each gravitational mode. And so look at here, this is already 1 over r times 1 over r. But here in addition, there are two derivatives. Here in addition, there are two derivatives. So overall, this is 4 derivatives times 1 over r squared. So overall, just by dimensional argument, it's 1 over r to the 6. So it's 1 over r to the 5 times the Newtonian potential. So we already know that finite size effect for spinless black hole are 5pn finite size effect. So a surprise is that the coefficient of that term in general relativity is 0 for black holes. It's not 0 for neutron star, but for black holes it's 0. This is a bit less of a surprise that in recent words to try to explain why that is 0 in terms of Gaussian symmetry. I don't want to enter into that, but this is just to tell you that I mean general relativity predicts not only the geodesic motion but also the effect of finite size, and those can in principle be tested. Not with present data because as you can see it's hypercompatible order, but luckily with the third generation of LISA we can see this hypercompatibility and there. Look, this is a black hole because this coefficient measured is 0. This is a neutron star with that and that coefficient. With the double neutron star that we saw with one of the double neutron star that like also was possible to measure a little with some precision this coefficient for the neutron star. And it was possible to recast it into a bound over the equational state of the neutron star. Because that coefficient for the neutron star is definitely not 0. For black holes in GR, it is. Okay, and so the broad picture is the following. We have exchange of gravitational potential modes between two particles, but then we also have to add the fact that in the far zone theory, we have the two particles that collapse to one, they are seen from far away, we see it as a composite object, but this composite object can self-interact. It can also emit, but in this talk I will not talk about emission. So basically the total of the dynamics will be given the total of the conservative dynamics, just because I mean of course we need to compute also the luminosity function, but just for the sake of this talk, let's focus on the conservative dynamics. The conservative dynamics will be given by exchange of potential modes and the exchange of radiative modes. Basically, here, it's hidden. If you expand this word line action, this is the time. So here is hidden coupling to gravitational modes, which are longitudinal, and here is written the coupling to radiative modes, also longitudinal modes, because see H00 and H0I are not radiative, but the far zone really encodes the coupling to radiative modes. This is something natural, like in electromagnetic, you have the Coulomb interaction and you have photons. Coulomb interaction mediates interaction between charges and the photons mediate radiation. In gravity, you have the same. You have Coulombic type of interaction that mediates, you know, the potential of the Earth, Sun, and so on. And you have gravitational waves. So the gravitational dynamics is mostly given by the interaction of these near zone potential modes, but radiative modes that can be emitted and reabsorbed also play a role. And you may think, oh, wait, but then, so basically this is something that in QCD was very well known. Usually, exactly in QCD, where this theory was inspired from, people usually split the region of momenta of the modes that are exchanged between the two particles in a region which is hard, soft, potential, and radiation. And basically, the two regions in which the momenta which is exchanged is of relativistic type, which is basically is so strong that it can give a hit to this particle, so that this virtual particle can have a non-negligible contamination from a particle-antiparticle state, and those are the quantum processes. And then there are processes in which this momentum is so weak, so low, that the recoil of the source is basically negligible. And basically here there's no quantum field theory propagator from this particle, because there is zero contribution from the antiparticle state. And you can guess that this is exactly the case of gravity. You know? Gravity exchange gravitational modes, but you never, ever to include the effect of antiparticles or anti-black hole here, just because the black hole is infinitely massive. So this diagram is classical in our theory, because here there's no propagator, there's no quantum propagator from this particle. This is a classical source and sink of modes. And if you don't believe it, one of the exercises that I give to my students, I mean, take the diagram in quantum field theory. Imagine that this is an electron exchanging a very high momentum graviton, and take the limit for the mass of the electron to go to infinity. You will see that this diagram is a classical piece. So, for those of you who did the quantum field theory and you were told that this diagram is quantum, this is wrong. This diagram is also quantum. It's not fully quantum. It contains a classical piece and a quantum piece. And the classical piece is all what survives when you take the mass of this particle to infinity. Or equivalently, if you exchange very soft potential gravitons or photons. This diagram is really quantum, because basically you have a loop of gravitons, and here, even if you exchange a very small amount of momentum, here you have a loop over this momentum, and this can reach arbitrary high values. So this is really quantum, so will not be considered in our computation. This will be quantum correction to the two-body potential. But two-body potential, two black holes, you can imagine the angular momentum of two black holes is 10 to the 80 in h-bar unit. So we want to keep only the classical interaction, and this is classical, because there is no propagator here for the massive. And in this formalism, this come out naturally. If you want to do this computation in quantum theory, is a bit more involved, because you have to take the full relativistic amplitude and then go and pick the classical limit, which is to send the mass of the particle here. Okay, so what we do in practice? So in practice, we take basically this particle is feeding the potential of the other the potential source by the other particle, and vice versa. What is the potential source by the other particle? Well, it's the Green function of the gravitational field times the energy momentum tensor of the other particle. No? In the lowest order, the energy momentum tensor of the other particle is just its mass. So basically, we put the Green function times the mass of the other particle. And now we do one crucial simplification. So this is the Green function, k squared minus omega squared, just the inverse of the box. The box in Fourier space is k squared minus omega squared. The Green function is the inverse of it. Modulo this I epsilon, that doesn't matter. And then we say, look, omega is much more than k, and so we expand it. Omega is the time component of the momentum which is changed. And so this is basically the approximation that defines the near zone. In the near zone, you say that the potential that are exchanged not only are taking very little momentum from the big massive guy, but they have a time component which is negligible with respect to the space component, so I can Taylor expand. So be careful, you see, at the end I integrate over all case. Okay? So this cannot be the full story, no? Because I integrate over all case, k here can go to 0. So when k goes to 0, it's very difficult for me to justify this expansion. But let's close our eyes to this difficulty and say, okay, look, I buy that the expansion of the green function gives me the contribution from potential modes. And then you do this, and then you do, then all the omega appears at the numerator, then it's easy to do the omega integration. This omega integration I do by parts is like a derivative with respect to T1, derivative with respect to T2. But then I know how to do the omega integration, and this gives me just deltas. So you see, I recover the instantaneous interaction between the two particles, which is the Newtonian, plus corrections that involve the derivative of the trajectory. So the full green function, that of course is relativistic and invariant, so must involve retardation effects, is actually traded for an approximate green function that involves action at distance plus derivative of the trajectory. Okay, so this is a perturbative result that recovers the fully relativistic result, but of course it's valid only when this momentum which is exchanged is of the potential type. It's like, you know, the potential exerted by any massive object or any other massive object is not of the radiation type. If some object is emitting a radiation, then the radiation will have k squared equal to omega squared, so we can't do this approximation. This approximation is valid only for the potential. But then you have to keep in the back of your mind that this must be an approximation, cannot be the full story. First, because it doesn't account for additive modes that have k squared equal to omega squared, but even more importantly, because I'm integrating for k equal going to 0, and for k going to 0, this approximation cannot be correct. So for sure, I'm missing something here. And yet another way to see it is look at this. When I expand and I take the derivatives, you know, the term with the highest power of derivatives in the denominator is always the one in which the derivatives hit the velocity. So you get velocity, acceleration, derivative of acceleration. So eventually this term will have a huge amount of power of k in the denominator and only 2 power of k in the numerator. So this integral eventually will diverge in the difference. Okay, this, I mean, doesn't matter even if you don't know quantum field theory, just expand this, look at this. Here I have arbitrarily high power of k, here I have only 2 power of k, and I integrate for k going to 0. I mean, sooner or later, this must diverge. So again, this is another symptom that this approximation must break down. And it's better to so, because otherwise I'm going to be telling that all of gravity between the two bodies can be described by the exchange of potential modes, which is not true. And luckily, we really get an infinite, we really get an infrared singularity. So the fact that you get an infrared singularity is actually your friend, because if we just got the wrong result, but finite, you never realize where we were wrong. But since we get an infrared singularity, then we know that we're doing something wrong, and we know exactly where it comes from, the wrong. Okay, so, but until we get there, that it happens at 4 p.m., up to 3 p.m., this is all of the story of the interaction between the two particles. So, and actually, we actually demonstrated that up to 3 p.m., I mean, and not demonstrating now because I'm just giving you a sketch of that, but can be demonstrated that up to third post-Newtonian order, all of the interaction between the two bodies is given by the exchange of potential modes at instantaneously at equal time, plus correction that depends on the derivative of the trajectory. Okay. So, but then you think, okay, but how to recover the correct theory, the full general relativistic, which is not action at distance, which is action at retarded time without infrared divergences. Okay, the fix to recover the full general relativity is that I have to add the far zone processes, the processes that I sketched here. If I add these far zone processes where I exchange, I emit and reabsorb radiation, and I add them to near zone processes, the sum of the two is the full GR. This statement is highly, highly non-trivial. The demonstration of it is highly non-trivial, but it's true, and you can find demonstration in papers. Okay, so this is just to reiterate on the thing, on the retardation. So in general relativity, we have a particle that depends on the particle 2 at some earlier time, that depends on particle 1 at some earlier time, and so on. So what we have done with that small omega expansion to trade this general relativistic interaction for an instantaneous interaction plus derivative of the trajectory. Okay, I'm running out of time. So it's a good time to ask questions when
in terms of expansion dimensions, adding near zone and far zone, does this correspond to different regions of expansion dimensions?
Exactly. No, this is the method of region applied to gravity, and so we are expanding in The near zone and far zone correspond exactly to these two regions. The modes which are off shell and the modes which are on shell. These are the two regions. The nice thing is that we don't need to care, we don't need to put by hand the limits in the integrand. We integrate over all of the space, and we take this contribution when we expand for omega small, and we integrate over all of the space, and I will show you in a second how we integrate over all of the space to recover the radiation. We should right now.
So,
Yes.
going back to that previous diagram, I was curious this one. I was curious. It seems like the right-hand side. Are you fixing the orbit for all times?
Yes.
So this seems like a problematic thing. Whereas on the left-hand side, you have a picture that could truly be causal. On the right-hand side, the thing has to know forever that it's stuck in a circular orbit or whatever.
Well, what we need to know is that there exists an analytic function, and our results will depend on the analytic function that we can complete generic. So we just need to know that they exist. We don't need to specify what they are. So our results for the potential will depend on the instantaneous position and velocity and acceleration and derivative of acceleration of the particle. But there is a good thing, is that okay, but if you need to specify arbitrary high order of derivatives, then you lose predictivity. No, because whenever we hit a X double dot, for instance, in our effective Lagrange, then we replace it for GM over R. Okay, we replace it for that, and we know that we are making cutting at finite order. This is fine. So whenever we hit on a higher higher than first order derivative, that would screw up our predictivity. We replace it with the equation order, and so we recover predictivity. So yes, in principle, we lose predictivity because we include infinite higher order derivatives, but since we are working at a finite order, we replace the equation of motion and then we recover predictivity. So just by substituting the equation of motion, we are fine. We obtain a consistent theory. Of course, when you go to higher order, you have to be careful that the equation of motion that is substituted at the previous order now gets correction. But it's so consistent. I mean, as long as you cut in the finite order. Okay, so and this is a sketch of the proof of why you can integrate the green function in the near zone feature in the near zone disguise over all case, and integrate the green function in the far zone disguise over all case, and the sum of the two is the total result. So this is a kind of toy demonstration. It's not actual demonstration, but the real demonstration is several pages, but it encodes the main points. So the real integral that you have to do is you have to take the Fourier transform of the real propagator, the real green function. When you do the near zone approximation, you take this approximation. You sum over 1 plus omega squared plus k squared plus omega 4 to the k4. And so when you take the far zone approximation, you take the full propagator, but you are expanding the source. This exponential is no longer e to the a chi x, but is k times x, kx squared. Remember, because there was the multiple, so this x increase the order of the multiple, and this k increase the order of the derivative of the Riemann tensor. So you get 2 power of x and 2k is the quadruple couple to the Riemann. 3 power of x and 3 power of k is the octuple couple to one derivative of the Riemann tensor, and so on. So this is the far zone approximation, basically expanding the exponential, and this is the near zone approximation, expanding the propagation. And then look at the first line. In the first line, I'm just writing it tautology. I mean, just forget this is equal to 0 for the moment. I say there is a clear separation of scale. There is a near zone, so high k, and far zone, small k. And here I say that if I integrate over all k, my far zone approximation, plus over all k, my near zone approximation, and then I subtract them, this is equal to the total integral. So the first line is just a tautology. Okay. Now, first physical observation. At small k in the far zone, the full integral is equal to the far integral, just because I'm now cutting the measure of integration to small k, and so I minus f here is 0. And so I'm left with the integration of over small k of n. And when I integrate over only on hard k, then I is equal to n, because for large k, I can do this approximation. So now this piece is equal to 0. So I'm left with this. So an integral of n over soft k and an integral of f over hard k. But look at this. Now I'm on soft k. So on soft k, I can expand also the exponential inside n. And look at this. Here I'm on hard k. So I can expand also the propagator of f. And so I can expand this and I get this. I can expand this, I get this. So I get the same thing over all of the space. And in dimensional regularization, the integral of a monomial of k is always 0. The integral of 1 over k squared minus omega squared is not 0, but the integral of k to the alpha is always 0. So this is 0, and so I'm left with what I wanted to demonstrate. That the total integral is equal to the far integral plus the near integral. Okay, this is really a toy version of the demonstration, but it grasps the main idea of the demonstration. Is that the full theory is actually the far zone approximation theory integrated over all momenta plus the near zone approximation integrated over all momenta. Again, this is far from trivial. It's just a very toy simplified demonstration, but it grasps the idea that you get exchange of potential mode integrated over all case from 0 to infinity, and integration over far zone modes, so multiples with the full propagator, again integrating over all cases. Again, no, because if you say this k can be whatever, because I'm integrating over all k, this k can be arbitrarily large, and we know that for arbitrarily large k, the exponential cannot be approximated with the expansion. But because of this non-trivial cancellation that happens in dimensional regularization, this holds. And so the full theory is equal to far theory plus near theory. So now that we accept this, that the full theory is given. Yes, the only missing piece to have the full result is how to express the multiples of the far theory instead of the near theory parameters. Not the near theory parameters, I'm 1 and 2, and the distance between the two particles. And I want to express the quadruple, the octuple, and all the other multiples in terms of these properties of near zone theory. Well, I just couple a long wavelength graviton and to the binary system, and just look at what the fundamental theory tells me that this coupling is. I just couple this long wavelength graviton. This coupling may depend on the momentum of it, and I just expand this coupling in the momentum of the external guy. So if I take the momentum of the external guy to 0, I get the lowest order coupling, and then I take the first order into the coupling of the external guy, and I get the first order, and then of course this is just g to the 0 and g to the 1. Then you can add the interaction, can get g to the 2, g to the 3, and so on. So it's completely calculable, the matching of the far theory into the parameters of the near theory. This is the matching that you need to do if you want to do gravitational wave analysis. But if you want just to do the far theory and obtain generic result in terms of the multiple, you don't even need this. You just have your results in terms of the multiples. That depends on what is happening inside the binary system. But if you want to apply the far zone result to generic system, you don't need to do this. You just get your results in terms of multiples, and then you say whatever the multiple is, this is the result. And then you go and substitute the multiples with the actual theory you're looking at, the actual physical system you're looking at, and then you get more precise results in terms of the precise constituents. Okay, and so let's go back to the thing of the divergence. So the divergence doesn't happen when you expand the Newtonian diagram, but you expand this g to the 2 diagram. So this next to leading order. Okay, this is a bit technical, but basically what happens here, I have 3 propagators. So 1, 2, 3 propagators. This interaction vertex has 2 power momenta. I mean, this is p, this is pi minus k, this is k. This doesn't have to be p, but this is just schematic. I mean, it could be p, it could be k. The thing is that the full theory doesn't have infrared divergence, and it will be a complicated function of the trajectory of the 2 particles. In our simplified version, we expand the propagator in this omega over k. And so what happens is that if you just do the power counting, this term should already give you an infrared divergence because it's 2, 4, 6, 10, and this is 3, 2, 5, 3, 8. Yes, 8. And then the 4 derivative will give 2 power of k. So it's 10 power of k denominator, 10 power of k denominator. So this is the first time they give you an infrared divergence. This is another infrared divergence. So it happens that the coefficient of this the leading order infrared divergence is 0 because it's proportional to the derivative of momentum of the system. And so the third term that gives a non-zero infrared divergence is third post-Newtonian order with respect to this diagram that is already one post-Newtonian order. So at fourth post-Newtonian order, we have the first appearance of infrared divergence. So we have the first proof that we need to have a complementary effect from the far zone. Just by power counting, it would appear at 3 pn, but by power counting, you don't get the pre-coefficient. The pre-coefficient happens to be 0. Okay, so what happens is that you do the computation of this divergence in the near zone, and then you add the contribution of the far zone, then you get the two divergences exactly compensate, and then you get, then I will show you in a second how to compute this object here, but let's just skip the result. So you get a divergence from the near zone, a divergence from the far zone, and of course the divergence from the far zone will depend on the multiples, cannot depend on the individual, the parameter or the individual components of the binary, because the far zone doesn't know the individual components of the binary. But look at this. From the point of view of the far zone, the divergence is the UV one. This is the standard thing that you get in particle physics. No, when you get to a distance that is close to the size of your particle, of what you thought to be the fundamental particle, then you get UV divergences, and you get the appearance of spurious parameter, this recurring parameter mu. But then, since we know the near zone theory, which is the exact UV completion of the far zone theory, when you add the two, you get the infinities disappear, the spurious mu function disappear, and then you get a logarithm, which is physical, and it's just the logarithm of the omega, which is the time behavior of the quadrupole, times r, which is the distance between the two objects. So you get a physical logarithm, which is dependence on real parameters of the system. So this is really a prototypical, I mean, in the standard model of particle physics, we get all the time, divergences in UV divergences. And we know the coefficient of the logarithm is physical, and then the final piece is not. It depends on what UV completion we have. This is a kind of toy model, I mean, not really toy model, it's really a physical model in which the UV completion of the far zone theory, it's a physical theory that we completely have under control. And we realize that the divergences goes away because they were just due to our incomplete knowledge of the short distance of our source, and all spurious scale goes away, and you get physical logarithm to the fact that the problem, the dynamics of the problem tells you that this happened. So this happens for the short distance singularities of the far zone. The far zone cannot have any long distance singularity because the far zone is already theory long distance. If it fails a long distance, that it means that it doesn't apply to physics. It means that we didn't understand. On the other hand, the near zone can fail at a long distance because we are failing to include the relative degrees of freedom when you include your safe. But the near zone can have UV divergences that are due to the fact that you are neglecting the finite size of the object. So since up to 5 pn we know that the black holes can be treated as point-like, all the UV divergences that we meet at 3, 4, 5 pn must be spurious, and indeed they can be gauged away, just a coordinate transformation, and they go away. We have shown it explicitly up to 4 pm. Okay. The other thing you can do is you can treat the far zone theory alone. So say, okay, I have the far zone theory. I know that I cannot extend it to arbitrary short distance, but I know that the logarithm is physical, and you can do a renormalization group resummation of the logarithm in the far zone theory, and you obtain results which are valid at all ordering perturbation theory. That this is a nice exercise that shows the solidity of the theory, and you say, oh, well, but how can you check results at all ordering perturbation theory, since anyway we have this computation are perturbative? Well, because we can check with the self-energy results that are non-perturbative in G, but are perturbative in another parameter, which is the mass ratio to particles. Okay, this was just an excursion. Okay, so then you may think, okay, but then this picture can lead us to compute everything, because we just add the near the far zone. Since near zone alone and far zone alone, each of the two is simpler than the full theory because of this approximation. In the near zone, I approximate this potential, and so I'm left with this integral. In the far zone, in the near zone, I approximate the propagator, so I'm left with this integral. So I can move on. So that's why people go to 5pn. So to get to 5pn, there was only one master integral, new master integral that we had to compute, and actually it was already computed numerically. This was a 4-loop self-energy diagram in a gauge theory that was computed numerically, and we fit to a very reduced sense of analytic number of transcendental number, an analytic formula, and so with the computation of only one master integral, basically one highly non-trivial master integral, we were able to push the knowledge up to 5pn, so up to 5th perturbative order beyond Newtonian physics. Basically, there's no obstruction apart from this non-trivial master integral, apart from the fact that you have to be careful in adding far zone contribution to the near zone contribution. Okay, so what are the far zone contribution? As I said, the far zone contribution you must collapse the two particles to one, and you cannot endow them with the individual degrees of freedom, but just global degrees of freedom. So total mass, total angular momentum, total quadrupole, total octuple, and so on. So the leading order diagram you can think of is quadrupole. So you cannot have mass or angular momentum, because angular momentum mass are conserved. So this emission of this radiative mode should have omega equal to 0, because a conserved mass cannot emit omega different from 0 radiative mode. So this is the leading order QP. And if you do this, you realize that it doesn't give contribution to the self-energy, it just gives contribution to the flux. Actually, this is the flux under these guys. And then you take this term gives a contribution to both the flux and the conservative energy. And then you go to higher order, you get a radiative emission of Q, radiative absorption, and then double scattering with the static potential. So here there is a technical point that arises, that if you want to use the particle physics method of straight away, you want to use Feynman boundary condition, and Feynman boundary conditions are wrong for this system, because this guy emits one radiative modes and then it absorbs. So you should use retarded advanced boundary condition, which are not Feynman boundary condition. So using Feynman boundary condition is wrong, but because of this identity, basically Feynman and retarded advanced boundary condition, they're all solution to the box equation with different boundary conditions. What we should use are the retarded boundary condition and not the Feynman. But what happens is, as long as you have only one emission and one absorption, so the omega which is emitted must be equal to the omega which is absorbed. So you basically get the square of a Feynman Green function with the same omega. This is a mathematical identity. It just happened to be so. And so basically, the square of a Feynman just reproduces the exact result as the square of an advanced plus the square of the retarded. There is this mismatch, but this mismatch is 0 because this is the Waldman function. The delta plus and delta minus have separate support. So when one is 0, the other is not 0, and vice versa. So this is 0. Sorry, here I missed the I. And this is an imaginary contribution. So the real part of the Feynman square is the same as if you use the correct boundary condition, just by accident. So as long as processes with only two radiative modes, one emission, one absorb, are involved, we are fine with the Feynman boundary condition. When we go on to higher order process where more radiative modes are involved, like for instance, if this mass here is replaced by another quadrupole, then we could have here 3 radiative modes. So this would have one frequency, this would have another frequency, and this would have the sum of the two. So this identity then does not hold anymore. And so we have to use a different framework, which is not the standard framework of particle physics with the Feynman boundary condition, but we have to change the boundary condition, and this will include complication, and we are still struggling. But I guess Gabriel made a step of we will talk about it next week. So okay, I'm pretty much done. So this is the Q. Sorry, what's the Q? Tilde is fully transformed. So this is the Feynman Green function.
The last one is some are tilde, some are not.
Sorry, it's just a mistake. Yes.
Okay.
Yeah. At some point, I probably got distracted when I was writing this, and then
Because I'm confused like wow.
So there is an I missing here. There is an I, and this is all tildes. So basically, the Feynman green function of the same, this is crucial, that the two green functions must have the same omega. And this is the case because you see they scatter over a static curvature, so it doesn't change the omega. Then it's equal to advanced plus retarded, which is the physical one, plus this is 0 because the delta plus and the delta minus and they have no common support, and there is an I missing here. So, and this is an imaginary part. Basically, these imaginary parts give you the effect that if you cut this diagram, then you get basically the emission. When you use advanced retarded boundary condition, you don't get the emission. You can see also here because the retarded ones are purely real. No? Delta plus and delta minus go once into the other by complex conjugation, and then there is an I. So these are real, and this is not real, not imaginary. This is complex. This is exactly the complex. There is an I missing again. This is exactly the imaginary piece that gives the optical theory. But for the real part, they are exactly the same as long as two propagators with the same omega are involved. And so we can do this computation quite straightforwardly. What is not straightforward to do the computation where here you have a dynamic source which has a retarded propagator and not a static one. And that's what we are struggling with the last year. Okay, and this is the summary, pretty much on time. So, okay, so this is a efficient method. It's not the method, it's not the only method. It's one method, not the many methods. So the velocities are completely under control and well understood. Going to higher order, the main bottleneck is master integral. Actually, not only that, this formula is the number of diagram explode exponentially, but you can think that going to the computer you can handle that. Then the real principal problem is higher master integral. So up to 5 PN, we only had one non-trivial master integral. At 6 PN, there have not been examined all of them, but surely there are new master integrals. So the 6 PN has not been done completely. So there is this problem of diamond proliferation. That means that you really have to automatize things very nicely. Otherwise, you are swamped by tens of thousands of diagrams. You don't want to do it by hand. And then again, whenever you have up to 2 radiative modes, things go smoothly. When you have more than radiative modes, in principle, we have a framework to treat them. It's just for the init formulas for Kelvin variable formulas. So in principle, it's all there. In practice, it doesn't turn out quite correct. So we're still working on it. And that's it.
Questions? All questions? I have actually 2 questions. One is about the master integrals. Are they always essentially zero scale integrals?
Yes. Basically, you have.
So there's essentially just direct computation.
Yeah, basically, in this approximation scheme, they all boils down to where is it? To this sort of diagrams in FT. Basically, you have a momentum flowing in and a momentum flowing out. These are self-energy of the gluon. So you have only one scale. This is really the Euclidean space 3-dimensional, because these are the near zone, and so it's just P square or S, fully whatever, and then you have all sorts of. This is for the near zone. The nice thing is the far zone are more complicated, but they kick in already 4 PN. So until you get to this level of complication in the far zone, I mean, you have more problems.
My other question was that we use renormalization to get rid of some defaults. Coming from particle physics, I would connect renormalization to quantum effects.
Exactly, that's the tricky point. The normalization is not a quantum effect; it's a field theory effect. Basically, what we get here, yeah, that was very puzzling. But when we first saw it, actually, it wasn't us who basically, yeah, they show it first. This renormalization. Basically, what the diagram that gives you renormalization is, I will draw it. Is this one? Basically, again, in the near zone theory, all the UV divergences are spurious, because we know that up to 5 PN, which is what we have investigated so far, there's no finite size effect. So you can really treat black hole as point blank. Again, forget it. So the real UV divergences that you get are in the far zone. So this is the composite object. When it's scattered twice over the, sorry, this is the information. When it's scattered twice over the static curvature of So this is the radiative mode emitted by the dynamical quadrupole, and this is twice two insertion of the constant curvature. So, and this gives a UV divergence, which is physical, because it really calls to the fact that you are missing some contribution from the short distance behavior of your source. And when you do that, again, this is classical, because here there's no propagator. This object is just a source on sink of gravity. There's no propagator of anti-black hole of involving black hole anti-black hole. So we get a purely classical renormalization. It's really due to the fact that you should open up here the source and see what is happening there. But you can do two things. No, why higher dimension operator? No, you do get a UV divergence, and then if you know the UV completion, because we do know it's the near theory, we just compute the near theory, we sum the two, and there's no divergence. Or if you forget that you know the near theory, you just keep this, you keep the logarithm, the finite piece, it's scheme dependent, you don't want to make a fuss out of it. You keep the logarithm and you say the logarithm is physical and will appear. And so you can use renormalization group evolution to get, for instance, the leading log energy at all orders, and this matches with the self-energy things. So, but this is a classical renormalization group flow. I mean, this is one of the misconceptions, that divergences, renormalization group, Feynman diagram, loops are quantum. No, they are field theory that contain both a quantum and a classical piece. And the nice thing is that in the infinite mass limit, when this mass is much, much larger than the momentum exchange here, the classical part is the only one that survives. There's no quantum part in the limit m going to infinity. Again, I don't have a slide on that, but this can be demonstrated. Basically, the demonstration, I mean, it's not a demonstration, it's argument of causability. You remember, when you do the Fourier transform, what you should really put, you should put an H bar here. Okay, because if this is the momentum times length is not dimensionless. Okay, and so whenever you have a E square minus omega square, for instance, for this propagator, you should expand it and keep only the leading order in P over M. Just because higher power of P will give you higher power of H bar. Okay, or the other way to see, suppose that P is not a momentum but is a wave number, then this is really dimensionless. But then P, if this is wave number, then P and M, then they don't have the same dimension anymore. P and M over H have the same dimensions. And then you clearly see that when H goes to 0, M blows up. And so you should really keep only the leading one over M order. So the non-relativistic limit and the classical limit are the same. And they really correspond to the fact that what you exchange is really another scale with respect to the scale of the mass. Of course, when you go to electrons that are relativistic and the photon exchange, so the same order of the mass of the electron, then quantum physics kicks in. You cannot do that.
Thank you.
No, thank you, Riccardo.
I think the biscuits are still there, just include.